The semi-submersible. It's simultaneously one of the most useful and, well, frankly, one of the most bizarre-looking structures in the entire offshore world. If you've ever actually seen one of these titans out on the water, you know they look almost like a mistake of physics. But by the end of this explainer, we're going to discover exactly why this completely absurd shape is actually an absolute marvel of engineering.
So just thinking about the overall shape, it completely validates your visual confusion, right? Why build a multi-million-dollar structure that looks like this? You have this massive, incredibly heavy deck structure, literally weighing thousands of tons, perched way high up in the air on these relatively thin columns. And those columns connect down to these enormous box-section pontoons that sit mostly submerged underwater. It completely flies in the face of what a traditional boat is supposed to look like. It almost looks top-heavy. But the brilliant minds who designed these vessels, they weren't trying to build a conventional boat. They were trying to solve a very specific problem that happens out in the open ocean.
And to really understand that solution, we have to talk about the physics of the ocean itself. When you look out at a stormy sea, the wave action on the surface is just incredibly violent and chaotic. It's a massive transfer of energy. But here's the secret. That energy is almost entirely concentrated right at the surface layer. If you travel just 20 to 30 meters down, the water is remarkably calm. That wave energy just dissipates incredibly rapidly with depth. So if you want a really stable platform, you don't want to be fighting the surface. You want to bypass it entirely.
Okay, let's dive into this. A semi-submersible takes full advantage of this physical reality. It puts the vast bulk of its buoyancy, those massive pontoons we just talked about, deep underwater, right down in that calm zone where the wave motion is minimal. Meanwhile, the main deck is lifted high above the cresting waves, and what connects them are those vertical columns. Because those columns are relatively thin, there's just minimal surface area for the chaotic surface waves to actually crash against. The result? You get a platform with truly remarkable stability, even in severe weather.
Now, let's look at a specific engineering term: water plane area. This is simply the cross-sectional area of a floating structure exactly at the waterline. So imagine taking a massive laser and slicing horizontally through a vessel right where the water meets the hull. The area of that slice? That's your water plane area. The semi-submersible is specifically designed to have a tiny water plane area. That literally means there's just less physical surface for the waves to push against.
Let's see how this builds our understanding when we compare it to a standard ship. A traditional ship floats with its entire hull resting right at the waterline, so it has a massive water plane area. When a heavy sea rolls in, those waves have this huge flat surface to push against, which causes the ship to roll, pitch, and heave violently. A semi-submersible, with its colossal capacity to consume water ballast and displacements of up to 170,000 tons, well, it has almost none of that problem. It presents essentially an immovable object to wave action in anything but the most extreme conditions.
Section 1. Form follows function, the 4 variants of the semi-sub. Because this physics principle works so beautifully, engineers have actually adapted it into 4 distinct variants. First up is the heavy lift. Take vessels like the Harem-Athial, for instance. These are the absolute muscle of offshore installation. Crane capacities have grown to a staggering 14,000 tons in a single lift. To keep from tipping over while swinging that immense weight, they use highly sophisticated, rapid-acting ballast systems that instantly counter the shifting load. And they do all of this while maintaining that incredibly stable baseline footprint.
The second variant serves a different but equally crucial purpose: accommodation. These are commonly known as flotels. You see, a standard offshore platform might normally house around 200 people, but during a major maintenance turnaround, you suddenly need 500 or more. You obviously can't put them all on the fixed platform, so an accommodation semi-sub moors right alongside, giving the expanded workforce a stable, safe place to sleep and eat in peace, even during a brutal North Sea winter storm.
The third, and probably the most common variant, is the drilling semi-sub, or MODU, which stands for Mobile Offshore Drilling Unit. While jackup rigs are restricted to shallower waters of around 120 meters, semi-subs have absolutely no such limitations. They operate in water depths ranging from 100 meters all the way down to 3,000 meters and beyond. They also offer a massive amount of deck space for storing heavy drill pipe and well test equipment. It's also worth noting here that the Deepwater Horizon, which is tragically famous for the 2010 disaster, was a semi-submersible drilling rig operating in deep water.
And this brilliantly illustrates our 4th variant, the Floating Production System, or FPS. Here, the semi-sub isn't just drilling a well, it's actually processing the oil and gas long-term. It sits high above the water, connecting via flexible risers all the way down to subsea wellheads on the ocean floor. We've seen a massive growth in these systems in areas like the North Sea, West Africa, and the Gulf of Mexico. This is especially true where ultra-deep water makes building fixed steel platforms practically impossible.
So the absolutely crucial point here is understanding the specific trade-off of using a semi-sub for production. On one hand, its unmatched stability makes installing and running topside process equipment much more straightforward than on a ship that's constantly rolling around. However, there is a massive catch. Since the hull design is mostly just thin columns and submerged pontoons, there is almost zero built-in storage capacity for crude oil. Unlike a concrete gravity-based structure, there are no massive void spaces to fill. Therefore, a production semi-sub absolutely requires an external pipeline to export the oil, or it needs a separate storage vessel moored nearby to hold all that crude.
Section 2. Station Keeping, Mastering Dynamic Positioning.
Whether a semi-sub is lifting 14,000 tons or drilling in ultra-deep water, it has to stay exactly in one place. And you can't always just drop massive anchors, especially when you're thousands of meters deep. So they use this hidden technological magic called dynamic positioning, or DP. Let's walk through this relentless feedback loop. Step 1. The computer gathers precise location data using GPS and seabed acoustic transponders. Step 2. It calculates its exact target offset. And Step 3, it automatically fires a network of azimuthing thrusters around the submerged pontoons to perfectly counteract the wind and waves. It can literally hold a rig within a few meters of its target, even in a raging gale, keeping the delicate drilling riser perfectly intact.
So, we've seen how the semi-submersible leverages the physics of the ocean to engineer its way around the chaos of the surface. It is a brilliant, stable, highly adaptable platform. But it leaves us with a massive logistical puzzle. If you were producing oil in an isolated, ultra-deep-water field thousands of miles from a pipeline, and your incredibly stable semi-sub has no room to store the crude oil it brings up, what exactly do you do with millions of barrels of oil? That specific limitation paved the way for the offshore industry's ultimate workhorse. But to see how that problem was solved, you'll have to join me in our next explainer, where we dive into the floating production, storage, and offloading vessel, the mighty FPSO. Until then, keep asking questions, and I'll see you next time.